All right, let's take a look at section 3.3. We've got some techniques of derivatives or techniques of differentiation, just some different wording there for you. So we're going to look at what's called the generalized power rule. So this is when you have a function, it could be a polynomial, but the generalized power rule works for any values that are powers. So for the generalized power rule, what we are going to do is we are going to look at a setup where we have a function, f of x. And again, this is just Euler's notation, function language here. F of x equals x, and we're going to raise it to a power of n. Now, n, I've stipulated over here, is a member of the real number set. So we're going to take the derivative here using a technique called the generalized power rule. So in order to take the derivative, first off, we need some derivative notation. Since we're already in function language, I'm going to make this f prime of x. That tells the reader I've taken the derivative of f. So I have f prime of x here. F prime of x now will equal, I'm going to bring the power to the front. So n was the power, so now it's going to be n times x. If there happened to be a coefficient other than 1 here, I would take n times that coefficient. Now, I've still got the x here. Now, my original power was n. I am going to decrease that by 1. So our derivative here, f prime of x, equals n, the original power, in this case times x. If it would have been a coefficient, it would have been n times the coefficient, then times the x. And then I decrease the power of whatever x was 2 originally by 1. So in this case, it's n minus 1. Now that is the generalized power rule for derivatives here. Okay, now that's the first derivative. We can always take the derivative again. And I would note that, again, we're in function language, so I would note that with double prime. 2 notches next to the f, f double prime of x. Again, I'm going to bring that power to the front, n minus 1, and then I'm times n, and then I'd have x, and then I'd have n minus 1, minus 1 again. I'm decreasing the power by 1 every time I take the derivative. So from the first derivative to the second derivative, we decrease it by 1. So we end up with n minus 1 times n. Yes, I could distribute the n over the n minus 1 times x, and now this becomes n minus 2. And that is the second derivative to the original function, f of x equals x to the n. Now we could take the derivative again. I have not stipulated what value n is, other than it is a real number value. Okay, so usually when you get to 0 as a derivative, you would stop. But again, that would only work if you had an integer value for the original power. Okay, and not everything in mathematics is clean like traditional polynomials. Okay, so that's the generalized power rule. Let's look at a couple examples and see this into play. Now, one of the things that we have to remember about derivatives is that derivatives are limits. They come from that difference quotient. The limit as h goes to 0 of f of x plus h minus f of x all over h. So again, derivatives are limits in theory. So when we're working with them, if we do have to take the derivative of a sum, it's going to be the sum of the derivatives, okay, given that the derivative exists. And again, it's dealing with limits, so we could add those two together. So I'm looking at f of x equals 5x squared plus 2. Now, generally speaking, that's a quadratic. That's a parabola from Algebra 2. Okay, so I want to take the derivative of that. Again, I've got f of x, Euler's language, function language, so I'm going to note the derivative with the prime notation. So I have f prime of x equals, well, the first part is 5x squared. So just using the generalized power rule, I'm going to take that 2, that is the original power, multiply it times the coefficient. So 2 times 5 is 10. I'm going to keep the x there. Okay, and now I'm going to decrease the power by 1. So originally it was a 2. 2 minus 1 is 1. I'm not going to write the 1 there. It's going to just be 10x. And then I also have to take the derivative of 2. Now, 2 you could think of as a 0, in a sense, x to the 0 polynomial. So if you use the generalized power rule, I would have x to the 0 here. 0 times 2 is 0. So the derivative here is 0. So my answer for this first example, f prime of x equals 10x. Now, remember that the derivative is the slope of the tangent line at an instant. So if you're thinking about what we just looked at for this example, when we take the derivative of each part, when we take the derivative of 2, now in itself, 2 is a horizontal function, it's a horizontal line, its slope is 0 everywhere. So when we take the derivative of 2 and we get 0, it should not be any mystery. Okay, let's look at example 2. Again, we're in function language, f of x, Euler's notation. So I want to take the derivative. I'm going to note that with my prime sign. So I have f prime of x equals, well, the first part is 2x to the 4th. Okay, so now I'm going to say 4 times 2 is 8 times x. I'm going to subtract 1 from the exponent, so 4 minus 1 is 3. So I've got 8x cubed for the first part. Now I need to take the derivative of negative 3x. X is to the first. 1 times negative 3 is negative 3. X now is to the 1 minus 1 power. We always decrease the power by 1. 1 minus 1 is 0, so that means I don't have an x there, or x to the 0 is 1. So I've got 8x cubed minus 3. We still have to take the derivative of the 1. And again, just like in example 1 with the derivative of 2 is 0, the derivative of 1 is also 0, because again, that would be a horizontal line as well. So our answer here, f prime of x equals 8x cubed minus 3. And again, both of those in function language. Okay, well, what if we're in y equals language? So we've got y equals negative 3x. Now this x is raised to the 1.2 power. 1.2 is a real number. However, it is not an integer value here like the other ones we've looked at so far. Then we've got minus 4x plus 1. Okay, so another way to express the derivative is in the variable that it started with. So y is already here. So I'm going to note the derivative in this one with y prime. Okay, now I'm going to use the generalized power rule and the idea that the sum of the derivatives is the derivative of the sums. Okay, idea here, because again, they're limits. So I've got to say 1.2 times 3, and that's going to give us negative 3.6. 1.2 times 3 is 3.6. Okay, so the power rule states that I'm going to decrease the power by 1, which means it started off as 1.2. So 1.2 minus 1 is going to give us 0.2. So the first part of the derivative is negative 3.6 times x to the 0.2 power. Okay, now I've got to take the derivative of negative 4x. Okay, again, I would take the 1 times the negative 4 to give us negative 4. X is now to the 0 power because 1 minus 1 is 0. So that's just going to be negative 4. Lastly, we've got the derivative of 1. The derivative of 1 is 0. So we've got our answer here. Y prime equals negative 3.6x raised to the 0.2 power minus 4. And that is the derivative of the original function. No matter how elaborate the derivative is, it still serves the purpose as the slope of the tangent line to the original function at an instant, or at one x value. Okay, last one here. We've got y equals x to the pi power. X to the pi power. Now pi is an irrational number. It is a real number. It's approximately 3.14. Okay, so we can use the generalized power rule here. And again, in this case, we're y equals. Well, let's use a little different notation here. Something called operator notation. Okay, operator notation is the notation that I'm most fond of because it tells the reader what to do and it explains it in terms of the variables. Okay, so on the left side, I'm going to take the derivative of y with respect to x. So I'm going to write the derivative, and I'm going to put a little bracket. And in this bracket, in this case, on the left side, I'm going to put a y. So I'm taking the derivative of this stuff with respect to x, okay? And on the right side, again, on that left side, it's just notation there. It's just notation. I'm just using some operator notation to tell the reader that what I'm doing. So I'm taking the derivative of y with respect to x. On the right side, I'm going to use that generalized power rule. I'm going to bring the power down times the coefficient. Pi times 1 is pi. Then I'm going to have x, and in this case, I'm going to decrease by 1, and I'm just going to write it as pi minus 1. That's the power. Pi is about 3.14 minus 1, so now we're at about 2.14 for that power, but even though pi is a real number, we're still going to treat it with the generalized power rule. So we've got pi times x raised to the pi minus 1 power, and again, that's in operator notation. Because there wasn't anything else other than y here, I'll just rewrite it as dy dx, and that's going to equal pi times x raised to the pi minus 1 power. And that's our answer, and then that one is in operator notation. Okay.